Hi, welcome to the third video on the Analytic Geometry series. So last time we've talked about circle as one of the conic section. Another is we've talked about parabola as one of the conic sections. So this time we'll be talking about the third, which is now the ellipse. So back then, we already know what an ellipse is. Something that we can describe as an oval shape is called an ellipse. Maybe one perfect example of the application of the study of ellipse is that the movement of the planets that revolve around the sun. So such movement follows a pathway called an orbit. So that orbit is described something as elliptical. So that's one of the applications of ellipse. So in order for us to further analyze and discover the concept of ellipse, we'll be first tackling the formal definition of an ellipse. So an ellipse is the set of points at which the sum of the distances from a point to two fixed points, and these two fixed points called the foci is a constant. So what does it mean? What are the keywords? It's actually a set of points. So if you pick a point on those set of points and you get the distance from that point to two fixed points, the sum of those distances is a constant. Those two fixed points are called the foci. So that's an ellipse. Okay, this time we will be discussing the components of ellipse in order for us to, number one, of course, we'll be able to identify if such equation is an ellipse. Number two, we'll be able to identify problems or solve problems involving ellipse. And number three, we will be able to find equations of an ellipse based on different orientations. So what are the two orientations of ellipse? For the two orientations is either the ellipse is elongated with respect to the horizontal axis or the x-axis, or ellipse is elongated with respect to y-axis. So it's either your ellipse is elongated this way or elongated this way. Okay. So let's suppose, for example, we have ellipse here which is elongated with respect to x-axis. So let's say this is our plane here. Suppose my drawing is perfect, I'm sorry. So this is my ellipse elongated with respect to x-axis. So we have points to remember here. So this is the point, these 2 points are the foci of the ellipse. So let's say this is the focus 1, the focus 2. These points here are the vertices of ellipse. So we have vertex 1 and vertex 2. Okay. The points here are the co-vertices, let's say E1 and E2. And the line segment connecting from vertex 1 to vertex 2 is actually, that line segment is actually the major axis. And the line segment connecting the two co-vertices is called a minor axis. So this is our major axis, and this is our minor axis. And the intersection of the two axes is called the center. We also have things to remember, like we have an imaginary line here. So there are two imaginary lines. They are called directrices or the directrix in singular. So let's say this is d sub 1 which represents directrix 1 and d sub 2 represents directrix 2. Okay, observe that back in the definition, according to the definition, an ellipse is a set of points at which that point, the distance from a point to two fixed points, the focus, it means, the sum of those distances are constant. Actually, if we pick a point here, let's say this is a point xy, so if we take the distance from this point to the two foci, that's actually the same as the length of the major axis. So say for example, your 2a here is the measure of the length of the major axis. So this is the length of the major axis. Major axis. So your 2b is the length of the minor axis. Your 2c is actually the length of the line segment connecting two foci. So this is actually c. So this is the length of the line segment connecting two foci. So if you take, let's say for example, okay, in order for us to get the equation of an ellipse given this orientation, so suppose for example, the center is found in the origin. So let's say this is the origin here on the xy plane. So if this is now the origin, so if we take this distance from a point we found on the ellipse, let's say this point here, let's say we label this as L1 and this is L2, and so this L1 represents the distance from this point to focus 1. This L2 represents the distance from this point to the focus 2. Your L1 plus your L2 is the same as the length of the major axis, which is 2a. In this example, in this illustration, our center is at the origin. So therefore, we're pretty sure that the focus is on the point, because of course, because the length of the two foci is, the length of the line segment connecting the two foci is 2c. You're pretty sure that the distance from the center to the focus is half of this, because c is the center. So technically, it's the midpoint of the two foci. So c will represent the length of this. So there, you're pretty sure that this is c0. And this point on the second focus is negative c0. Do you get it? So this is 0, 0, and this is xy. So using the distance formula, the length of L1 is actually the distance of this. So you have x sub 1 minus x sub 2, your x sub, x sub 1 minus x sub 2, your x sub 2 is c, so minus c squared, plus y sub 1, which is your y, minus y sub 2, which is 0 in this case, so you have squared, plus the square root of, this is now your x sub 1, this time your x sub 2 here is negative c, so you get plus c here, squared, plus y minus the y sub 2, which is 0, so you have y squared, equals, again, the same as the length of the major axis, so you have 2a. Okay, how do we simplify this? I have to be honest with you, I don't know if some mathematics teachers would agree this, but for me, if we do manipulations in algebra, there are certain rules. But I don't believe in techniques like how do we simplify that easily. Technically, there's no such thing as simplifying that easily. Because techniques are not actually meant to be taught. It's actually meant to experience. So if you have done a lot of experience on solving manipulations in algebra, then that would be easy for you. Because all of techniques, all of the solutions are actually the same. It's a matter of how you do it in the easy way, based on your level. So you can just simplify this by squaring both sides, or in my technique is that since they have two square roots on this side, it would be difficult for me because if I take the square of this side, you would eliminate the square root of this side, but there's a middle term that still expresses the square root sign. So what I do is I'll transfer this first to the other side. Before I'll take the square of both sides. Trust me, all the square root sign will be eliminated, unlike the other technique that I discussed earlier. So you will get this, you square both sides. So I'm not going to discuss the manipulations anymore because it's not algebra we're talking about, it's analytic geometry. If you have questions on how to get that, you can comment down there or you can message me. So doing some manipulations, I'll get this value. Okay, I'll get that value. Okay, now, before we continue with this one, let's again go back to this rule. Okay. Remember that 2A is the length of the major axis. Your 2B is the length of your minor axis. And your 2C is the length of the line segment connecting the foci. Okay, right. So, observe that the sum of the two L's, so the L1 and the L2 here, is the same as the length of the major axis. Now, this is quite the same as the square of the half of the major axis. So the half of the major axis is A, so the square is A squared. This is the same as the square of the half of the minor axis plus the square of the half of the length of the line segment connecting the foci. So technically, you have this equality here. It looks like the Pythagorean theorem, but it's not. So it's actually the equality on the distances of points present in this ellipse. So if I replace this, I will have a final equation of x squared over a squared plus y squared over v squared equals 1. So that's now the equation of the ellipse with a center at 0, 0. So your center here is at 0, 0, or the origin. And this is elongated with respect to the x-axis. Okay? So what happens if it's not elongated with respect to x-axis, but it's elongated with respect to y-axis? You do the manipulation again. So let's say if this is elongated with respect to y-axis, of course your vertex is here and here. Your focus somewhere here in this line. Your co-vertices are here. So they're actually transferred. So technically, you just transfer this one. The same manipulation, you'll arrive with this. B squared plus y squared over a squared equals 1. So this is elongated with respect to x-axis, and this is with respect to y-axis. That's it. Okay, so again, this is now the equation of the ellipse, elongated with respect to x-axis, and this will represent an equation of an ellipse elongated with respect to y-axis. Now, provided, of course, the center of these two equations are at the origin. Now, let's say, for example, what happens if the center is not in the origin? Let's say, for example, the center is not anywhere here but somewhere else. Let's say, for example, we have a point 1, 2 or a point 5, 6, or in general, let's say a point mn. So m and n are any integers or any real numbers. For example, consider this. Let's say this is your ellipse now. So this is where your center lies. So let's say the center is mn. So it's still pretty sure that what we are going to do is you assume the mn or the center as your second origin. Let's say you consider mn as your second origin. Although it's not the origin, but you assume that as your second origin. So if you pick a point here, let's say x bar and y bar. Why I'm using x bar and y bar? Because this is not the same as the x and y when the center is at the origin anymore. So I'll replace this with x bar and y. I'm pretty sure that x is actually x minus m. And your y bar is actually y minus n. Okay, so using the manipulation again, like what we've done earlier, we arrive with this x bar. I'm sorry. Yeah, this is x bar over a squared plus y bar over b squared equals 1. But take note, we are just assuming a dummy variable x bar and y bar in order for us not to be confused with derivation of equations that we've done when the center is at 0, 0. So instead of using this, we can replace this as x minus m squared, sorry, this should be squared, over a squared plus y minus n squared over v squared equals 1. So this is now the equation of the ellipse elongated with respect to x-axis, and your center is somewhere at mn, not the origin anymore. So your center here is mn, and it's elongated with respect to x-axis. So what happens when it's elongated with respect to y-axis? So the same process that we've done earlier, you just replace these, so you'll get x minus m squared over b squared plus y minus n squared over a squared equals 1. So this is with respect to y-axis. That's it. Okay, so we're done now with the derivation. We have familiarized already the components of ellipse. So let's recall again. This is x squared over a squared plus y squared over b squared equals 1. Or we have x squared over b squared plus y squared over a squared equals 1. So this equation is again when your center is at the origin. So these two will represent centers at the origin. But this is with respect to x-axis. And this with respect to y-axis. When I say with respect to x-axis, the elongation is with respect to the x-axis, or its major axis is parallel to the x-axis. So that's when the center is at the origin. So what happens when it's elongated? Yes, it's elongated with respect to x-axis, but the origin is somewhere at mn. So what we've derived earlier, that will be x minus m quantity squared over a squared, plus y minus n squared over b squared equals 1. And you for the y-axis, for elongation with respect to y-axis, you have x minus m squared over b squared plus y minus n squared over a squared equals 1. That's it. So let's say, for example, find an equation of an ellipse with center at 0, 0. one of the foci, let's say one of the foci is at point 5, 0, and one of the vertices is at point 7, 0. So how do you plot that? Or how do you get the equation of that? So it's pretty simple. You just have to plot this first, this given. So you have 0, 0 as a center. One of the foci is 5, 0. So somewhere here, let's say this is the foci. So somewhere here is 5, 0. One of the vertices is 7, 0. So somewhere here is the vertex. This will already tell you that the distance from the center to the vertex is 7, and the distance from the center to the focus is 5. So you already have the value of A and C. So how to get the B? So that's A squared minus C squared. So you'll get 49 minus 25. So this is 24. So therefore your B is square root of 24. Or via estimate, that's 2 square root of 6. So that's your B. So which means that, what's 2 square root of 6? So probably, let's assume this is 2 square root of 6 here. 2 square root of 6. I'm sorry. This is 2 square root of 6. So let's assume that way. Or you can just make your own, you just compute your own in your own calculator for you to plot on the graph. So you're pretty sure the other focus is in negative 5, 0. And your other vertex is negative 7, 0. So you just follow this. Just follow that. You just follow that, and so on. So that's your ellipse. I'm sorry I don't have a perfect drawing. So, but it actually looks that way. Okay, this time we're going to discuss another example of the problem involving ellipse. Okay. Given an equation 4x squared plus 9y squared minus 16x minus 54y plus 61 equals 0, identify its components and plot its graph. So how are we going to, before we start solving this one, how are we going to know if such equation is an equation of an ellipse? Okay, let's recall last time that in order for us to identify if the equation is a parabola, we have to check the variables. So the variables are x and y. So only one of them should bear the highest degree of 2. So either x or y. And the other one should have the highest degree of 1. In this case, you check all the variables, x and y. Both of them should have the highest degree of 2. So you have highest degree of 2 for x and y. And they're both positive. So this is both positive. These are both positive, regardless of the other component, of the other terms, rather. So this is an equation of an ellipse, since the highest degree of x is 2, the highest degree of y is 2, and both are positive. However, it's actually written in a general form. So when we say general form, everything is written there on the left side equals 0. Now, we'll transform this into a standard form of the ellipse. So in order for us to do that, we're going to group this. So I have here 4x squared minus 16x. I also have 9y squared minus 54y equals negative 61. For me to easily do that, I will factor this out. 4 times x squared minus 4x. I also have here 9y squared minus 6y equals negative 61. Then second is that you have to complete them in order for these terms to be expressed as a special product or a perfect square. So we have to convert these into perfect square. So let's recall back then in our elementary algebra. You have to complete the term in order for you to get the special product. So remember that x squared minus 4x, if I add this by 4, this becomes x minus 2 squared in your elementary algebra. So I'll just add this by 4. So therefore, on the left side of this equation, I added 4 times 4. So I also add this here, 16, which is 4 times 4. In order for you to preserve the equality of your equation. Same with this. You have y squared minus 6y. So if you add this by 9, this will be y minus 3 squared. So therefore, I add this by 9. So it seems that I add the left side of the equation by 81. So I also add here 81 to preserve the equality. So therefore, I can have 4x minus 2 squared plus 9y minus 3 squared. And this will bear a total of 36. Okay, so remember that the equation I have presented earlier, the equation of the ellipse, the right side is always 1. So I shall change this into 1. So I will divide both sides by 36 to make this as 1. So if I divide this 36, I will also divide this each term on the left side by 36. Okay? So I shall have x minus 2 squared over, this will become 9, plus y minus 3 squared, this will become 4. So this will become 1. Or I can change 9 into 3 squared. I can change 4 into 2 squared. So what does it imply? You already have your center. Your center is 2 and 3. So you have 2, 3. Your A here is 3. Your B is 2. So therefore, what's your C? So your C is simply C squared equals A squared minus B squared. So you'll have 9 minus 4. So you'll get 5. Therefore, your C is square root of 5. What else do you have to solve? The focus. So your focus 1. So your first focus is, by the way, where is your A? So, how this equation is elongated with respect to what axis? So, just check which of these terms has the highest value on the denominator. So of course, this is the highest. This is the higher, sorry. So 3 squared compared to 2 squared. So this shall be the A. So since A is the denominator with respect to x, so the elongation is with respect to x-axis. So therefore, your focus is, since this is your center, okay, let's start first with the vertex instead of focus. So your vertex is 3 units from the center to the right. So this becomes 5, 3. Your vertex 2 is 3 units from the left of the center. So that's negative 1, 3. Okay? So your focus is, that's measured as C. So that's square root of 5 units from the right of C, or from the right of the center. So that's 2 plus square root of 5, 3. And square root of 5 units from the left of 2, so that's 2 minus square root of 5, 3. So that's it. That's the focus. What are the co-vertices? So I'll just erase this portion here. So what are the co-vertices? So the co-vertices is, this is 2, your B is 2, so you have 4, 3. I'm sorry, should be on the top. So 2, 5, and E2 is 2, 1. That's it. Now remember that, as what I've mentioned earlier, the distance from the vertex to the directrix is the same as the distance from the vertex to the focus. So what's the distance between the focus and the vertex? So you have 5 here. This is 2 plus square root of 5. So from the vertex to the focus is 5 minus 2 plus square root of 5. So that's 3 minus square root of 5. So therefore, I will add these to the vertex. So therefore, your directrix is, your vertex is at the value x equals 5. So the directrix, the first directrix is x equals 5 plus 3 negative square root of 5. And your second directrix is x equals 1. So I shall have 1 minus 3 plus square root of 5. That's it. So how do I plot this one? So your center is 2, 3. So 1, 2, 3, 1, 2. So somewhere here is your center. Your vertex is 5, 3. So 3, 4, 5. So this is where your vertex. Another vertex is found on negative 1, 3. So negative 1, 3. So that's somewhere here. Okay. Your focus is somewhere here. I'll just estimate this. So that's 2 plus square root of 5, 3. So somewhere here. Square root of 5 is more than 2. So probably that's 4. More than 4. So somewhere here. So that is somewhere here. So this is your vertex 1. This is focus 1. This is your vertex 2. This is your focus 2. Your co-vertices are found on 2, 5. So that's 4, 5. So somewhere here. And 2, 1. So here. So you'll just have this. So your directrices is the same as the distance with this. So somewhere here. So your directrix 1. So this is the equation of x equals 5 plus 2 square root of 5. And somewhere here is your directrix 2. The equation is x equals negative 1 or I shall have negative 1 plus 2 square root of 5. And that's it. Okay, I have a question here. What happened if the length of the major axis and the length of the minor axis are equal? So let's say for example, the length of the major axis is m, and the length, let's say k, and the length of the minor axis is k. What happened? So if you're trying to figure that out, let's say this is the length of the major axis, this is the length of the minor axis. They're equal. So this is equal to this is equal to that, this is equal to that. Okay, so therefore, if the length of the major axis and the minor axis are equal, technically that's a circle. Because it looks like it's the radius here, so the radius is equal to that, this is equal to that, this is equal to that. So if you consider this as a string, so if you rotate that one, it actually forms a circle. So conclusion is, a circle is one of the conics that is a special type of ellipse. Therefore, all circles are ellipse, but not all ellipses are circles. Okay, so we're done with a series of example. So this is another example, but I don't have to solve on this one. I want you to solve on this and comment down there on your answers. Find an equation of the ellipse with center at the origin, and one of the vertices is located at point 60, and one of the endpoints of the minor axis or one of the co-vertices is at 0, 3. Sketch the graph and find the equation. So of course you cannot sketch on the comment down there, but you can write your answer on the comment. The equation on the comment. That's all. Okay, that's all for now. Thank you so much for watching. So we've done so far with a circle as a conic, parabola as a conics, and ellipse as a conic. So up next will be the next conic section, which is the hyperbola. So if you have questions, you can comment down there. Please subscribe to the subscribe button and see you next time. Thank you.